Well, today I'm going to talk about tensor decomposition, part one, and today I'll focus on non-symmetric tensors, and on part two on Friday I'll talk about symmetric tensors. You have notes together with the homework assignment, and I will give you updated notes before the Friday lecture. Okay, well, so what is a tensor? So McCullough's book on tensor methods and statistics gives maybe like 10 definitions of what a tensor is. I'll just give you two today of what a tensor is, and maybe you have your own favorite definition. So a tensor, well, is just a collection of numbers in a field. So F is going to be a field, and then a tensor is just going to be a multidimensional array of numbers. That's our first definition of a tensor. Well, you may like to have a slightly more abstract view of a tensor. So a tensor is going to be an element in a tensor product of vector spaces, and I'll tell what this is in a second. So A, B, and C are vector spaces over the field, and we'll call an element of the tensor space a tensor. So it's sort of a circular definition, but this vector space has a basis. Well, I need to declare the bases of my other vector spaces first, so these are going to have bases A1 to AM, B1 to Bn, and C1 to Cp bases. So then this tensor product space has basis AI tensor Bj tensor Ck. Okay, so it's a big vector space, and I've declared the basis for you. This means that I can write my tensor T as a linear combination of the elements and the basis. Okay, so two different views of a tensor. Tensor is just a collection of numbers in a multidimensional array, or it's an element of a tensor product space. Okay, so I want to stick with this abstract approach for just a little bit longer. So let's talk about this tensor symbol. So I can define this symbol tensor as a map . And again, it seems a little bit circular as written, but I hope that it'll be clear as we go along. So to find this map tensor product, just to take an element in X, an element in A, and an element in B, and map it to this element, X tensor Y, and declare a couple of properties. So we're going to declare that this product is F bilinear. That means that, well, let's do, this is number one, and then number two, tensor product is associative. Okay, so number one, just to recall what this means that if I take lambda x plus x prime, and I tensor that with y, this distributes, so this is lambda times x tensor y plus x prime tensor y, and then similarly on the other side. Okay, so this is 1. And this is for all x and x prime in A, for all y and y prime in B, and for all lambda in the field. So for us, the field will usually be real or complex numbers, but if you like to study a different field, that's fine. So I have an F bilinear map that I'm calling tensor product, and it's also associative. So 2 just means that if I tensor A tensor B and then tensor C later, that's the same thing as if I tensored first B and C together, or I'm not going to write it, I could have tensored A and C together first and then added B. So this means that this A tensor B tensor C makes sense. It makes sense to write the triple tensor product, even though I only defined it for 2 factors. Okay, so the outline for the lecture today is tensor basics. These are a couple of the tensor basics. If you're interested in some references, I recommend the new book of Professor Landsberg. There's also an article that was just published recently by Carlini, Grieve, and myself, 4 lectures on secant varieties. You have the archive identifier here, and then for the second lecture, I have a reference of myself and Ottaviani, eigenvectors of tensor and Waring decomposition. So those references are in your notes, so erase them. So now that everyone's here and seated, it's 9 in the morning, 9:10 in the morning, I want to give you an idea of what is tensor decomposition by audience participation. So what we're going to do is, if your birthday is in September, like mine, then I want you're going to say in a moment the word tensor. If your birthday is not in the month of September, then I want you to pick a random 2-syllable word, and that's what you're going to say. And we're all going to say our word at the same time when I say 3, and then I'm going to try to count how many people said tensor. All right? Okay, so you got the idea? If your birthday is not in September, say a random 2-syllable word. If your birthday is in September, say tensor. Okay? So on the count of 3, on 3, say your word. Okay? 1, 2, 3.
Tacos!
Okay, I think 7 people said tensor. I'm just guessing. I don't know if really 7 people said tensor. So that's actually really hard to do, right? I mean, if you're in an audience, if you're at a restaurant and somebody says tensor, well, I like tensor, so I'd probably look when I heard out of all of the noise of all the other things. So let's try it one more time. What we're going to do on Friday is something similar to the next exercise. We're going to add in redundancy to see if we can actually find out who said tensor and how many people said tensor, okay? So now I want you to say your word 4 times in a row, okay? So on 3, say your word 4 times in a row. 1, 2, 3.
Tensors, 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 tensors.
Great, so I think maybe 8 people said it, okay? I'm just guessing there's 70 people in the room, maybe 7 or 8 people have birthdays in September. So that's the idea. So there's lots of noise. We want to find the rank 1 tensors, which are the single people who said tensor, out of all of the noise, out of all of the other things that were said. So that's the idea. So given T and A tensor, B tensor, C, find an expression T is equal to now a linear combination. So sound waves add as they all arrive to my ears. So this is going to be a linear combination of S equals 1 to R, X sub S tensor Y sub S tensor Z sub S, and then X is R in A, the Y's are in B, and the Z's are in C. Okay, so find an expression. This means find the minimal R. R is called the rank. And then this expression is called a decomposition. Okay, so in this decomposition, we're looking for vectors x, y, and z, such that when we take their tensor product, write out that expression in bases, add up all of the expressions, we get a single tensor. And we want to recover these individual summands. We want to find the rank R, and so on. So we covered tensor basics. Maybe you think this problem is easy, so I recommend looking at a paper of Lemma and Hiller. The title is really easy to cite. It's called Most Tensor Problems Are NP-hard. So if you're wondering maybe why this is an interesting problem, most problems in linear algebra are polynomial time solvable, maybe matrix multiplication, so on is something interesting, but tensor problems are usually NP hard. So this problem that I wrote here, just count the number of variables and the number of equations that are involved in this expression, and you'll find that this is a really hard system of polynomial equations to solve, as John mentioned yesterday. But nonetheless, it's constant time solvable when we fix our vector spaces A, B, C, and our rank R. So why should we be afraid of NP hard? It's constant time solvable. So one goal of this lecture and the next lecture is to solve the smallest problems that we can solve for tensor decomposition and not try to find a general, necessarily algorithm to solve all problems. We would solve P versus NP. We're not trying to do that in these lectures. But we are trying to solve the smallest cases. But we need to sort of set an algebraic geometry framework for these problems that'll make it easier to study them. So since we're talking sort of in abstractness, a little bit about tensors, let's do one more basic thing. And now I will erase the outline. Okay, so vector spaces, finite dimensional vector spaces come with their natural basis that we've chosen. So we can define a dual vector space. So A star is just the linear maps. I prefer to write them alpha to the ground field. And then we have dual basis, alpha 1 to alpha m. And we have the duality is alpha I of aj is just the Kronecker delta function delta aj. So dual bases, dual vector spaces. So why do I need this? So I want to talk about tensors from the point of view of matrices. Go back to some familiar ground. Okay, so we could think about a matrix first in this sort of slightly more abstract view. So I'm going to think about the vector space A tensor B, and I'm going to take M inside of A tensor B. Well, this represents a linear map. Well, it actually represents two natural linear maps, so we're going to write one of them first. So let's write a map from A star to B. So how do I get a linear map out of my matrix? So, or out of my element in the tensor space? So M is going to be a sum I, J, scalars Mij, AI tensor Bj. So this is my abstract tensor, but I'm going to write it as a matrix by doing what I do in freshman linear algebra. So I want to understand a linear map, then I evaluate it on a basis, and I put the results in the columns of my matrix. I hope that we all remember this. So what is it going to do? This is my map. I'll still call it M. So M takes an element alpha I and maps it to, well, the sum over I. Well, let's make this an S so it looks different. Sum over I, sum over J, Mij, and then the alpha S eats AI and multiplies by Bj. So this is what this does. And so now my matrix in the S column is going to have, well, this expression simplifies a little bit because the Kronecker delta function. This is just the sum now over J equals 1 to N, M, S, J, B, J. So I'm trying to be careful with indices. So this is maybe counterintuitive. What goes in the S column, S, J. So the row index S is indexing actually the columns for this matrix. So this is the transpose of what you expect. Well, the transpose of what I might have expected. Okay, but I shouldn't have chosen necessarily A to be my favorite vector space. Maybe B was my favorite vector space. So let's write the other linear map. I'm still going to call it M from B star to A and do exactly the same thing. Beta sub S is going to go to the sum, now let me shorten this. This is going to be I from 1 to m, I, S, AI. Okay, so remember, the betas are dual bases, so then this is the matrix whose S column is M, I, S. This is the usual matrix that we would associate with these indices. So this is clear how to take an abstract vector in a tensor product space and write it as a matrix. Great. So we're going to do the same thing now for a tensor. We're going to use the fact that the tensor product is associative to define the notion of a flattening. So recall that I said, okay, A tensor B tensor C makes sense, but I'm going to write this as A tensor B tensored with C. So there's one more thing I want to do before this, I forgot. So we want to vectorize, borrowing from implied language, vectorize my matrix M. So I'm going to write M. The notation will be more clear in a moment. M lower C is going to be the vector after a chosen, well, M. This is M lower C now is going to be a linear map from A tensor B. Could have done the other thing. Go down to my field. I'm still calling my field F, so let's call this F. Okay, so I could have put all the vector spaces on the left-hand side of the map and mapped just to the ground field. So what this should be is a very long vector and then one row, right? Okay, so this is going to be M11, M12, dot, 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 M1n, bar. The bars are just spacers. And then M21, M22, M2n, down to M1 to M, Mn. Okay, so we can vectorize matrices. So we can actually matricize tensors, and that's what we're about to do here. We're going to matricize. And I don't really like this word, so I'm going to call it flattening. Okay, so matricize is taking a tensor and making it into a matrix, but I'm actually going to call it a flattening. So we're going to write T sub C as a linear map. Now looking at this space of this exactly the same way as we thought of a matrix as a linear map, like this. So I ignore the extra structure on A tensor B, think of it as a vector space, and now I can write a matrix by the same process that I did before. And just so I don't mess up the indices, let me write them. So we're thinking of our tensor as a sum over k, sum over j, sum over I, I, j, k, a, I, tensor b, j, and then I'm going to parenthesize here tensor ck. So this is the abstract thought of a flattening, and now I write it as a matrix. So remember, tensors, and for now, I mean, all of the properties we want to study are captured by a triple tensor product. So I'm still going to focus on three factors, well, three indices. So the first entry in my matrix is T111, and then I'm flattening every matrix that I see. Well, give me 1 second to write this out. It's a little bit long, but it's also in the notes. Okay, the first row of my flattening looks like this. So what stayed constant in the first row is the last index. All right? The second row looks like this. T112, T122, T1n2, T11, T2n2, Tm12, Tmn2. That's what the second row looks like, and then so on, all the way down to the last entry, T11P, T12P. Okay, so the flattening of a tensor is equivalent information of the tensor, but we're choosing to write it as a matrix. These blocks that I've indicated here are called the slices of a tensor. And maybe I'll index this by, okay, So the first slice, what's constant in this matrix is the first entry. It's T1. And then I leave the next two entries blank. This is T2 blank blank. And then this is Tm blank blank. Those are the names of my slices in this direction. Okay, so does everybody know how to take a three-dimensional tensor and flatten it? If you imagine your Rubik's Cube as being your 3 by 3 by 3 tensor, you're going to pick an orientation and cut it straight down like slices of bread and then lay them out next to each other. That's what a flattening is. Okay, so of course I can do this for all choices, just like I did matrices going to two different vector spaces. I also can define, and I'm not going to write them, but TB is going to be a map from A tensor C dual to B. TC is going to be a map from A tensor B dual to C. We already did this one. And then TA is a map from B tensor C dual to A. Okay, so I have three flattenings for a three-dimensional tensor, and I have many more flattenings for a multi-dimensional, more dimensional tensor. And, well, I chose bases to write all of these things, but the expressions that I came up with, well, what's invariant about what I did here? It's not the matrices themselves, but the ranks. So I'm going to collect the ranks into what's going to be called the multilinear rank. MR of T is equal to the rank of TA, rank of TB, rank of TC. Okay, so one thing that you hopefully remember from linear algebra is that matrices have many definitions of rank that all agree. Right? So the row rank equals the column rank equals the number of rank 1 summands needed to express it equals the SVD rank equals the number of non-zero eigenvalues counted with multiplicity. There's so many definitions of rank for matrices which agree. This is the first definition of rank which the row rank, column rank, and into the board rank don't agree. So let's see an example. Sorry to do so much notation first and then the example second, but so here's my example, the smallest possible example I could come up with where the multilinear ranks are not all the same. So let's take my tensor as A1 tensor B1 tensor C1 plus A2 tensor B2 tensor C1. Okay, so maybe you can see immediately what the multilinear ranks are, but let's just write down the flattenings and the multilinear ranks just so we're all on the same page. So TC, TB, TA. Okay, so what's this flattening? So I'm going to very pedantically number the columns just so we're really clear on what this matrix is. So the rows are indexed by A tensor C, elements, or A tensor B, and the columns are indexed by elements in C, right? So wherever I see, okay, 1, 1, 1, this means A1, B1, C1. I put a 1 here, I put the coefficient of that term here. And then there's only one other term, and its index is here. Okay? And all the rest of the entries are 0. So that's the flattening in the C direction. TB. Well, A and B are symmetric, so these two are going to be the same. But now I'm going to index TB by entries A tensor C, and then the columns by B. And this matrix looks like this. And then TA is the same matrix. Okay. Okay, so now we can compute the multilinear rank of this tensor. Let's see, 2, 2, and 1. Okay, so the multilinear ranks are not all the same. Why do I start with multilinear rank instead of tensor rank? So I think that this is perhaps the biggest dimensional reduction that you can make when you're first answering any question about a tensor. So if somebody gives you a million by million by million tensor, then you're going to have a tensor with more entries than the federal debt. But then you might say, well, do I really need that many entries in my tensor, right? So here's an example. Let's take another example. Let's suppose I just add up all the first basis vectors, and then add up all the first basis vectors in the next factor. Maybe it seems artificial to do this, but let's see what we get. So this is my next example. This is the all ones tensor. So it's certainly not sparse. It's completely filled with non-zero entries. But it's actually just lives in a one-dimensional space. So T actually lives in a copy of C1 or F1. Okay, so versus T, which is just a one-dimensional vector space, versus T inside of C, M, and P, which is possibly very large. Okay, so this is a large dimensional reduction. Okay, so if you're trying to solve a system of polynomial equations for a tensor problem, you should probably first reduce the number of variables so that you don't have to deal with the huge number of variables in the first place. So if it's possible to move your tensor into a space which has less variables, you're going to save time in doing your computation. Okay? Okay, so this brings me to this conference is about algebraic geometry and complexity theory. So what's the algebraic variety involved here is called the subspace variety. So the subspace variety, I've just shown you a few instances of it, so let's just okay, so the subspace variety indexed by R, S, and T is equal to, well, it's going to be the lines through tensors and PA, tensor B, tensor C. So rank is unchanged by scalar multiples, so I might as well work with lines through the origin. Okay, so this is going to be, I need there to be a subspace in each direction. And T actually lives in the tensor product of the subspaces. And the dimensions, A prime is R, dimension B prime is S, and dimension C prime is T. Okay, sort of a long definition, but it's the variety of tensors which can be written using fewer tensor variables, possibly fewer. R, S, T instead of M, N, P. Okay, so this subspace variety, if you want to test whether your tensor lives in the subspace variety, how can you test this? So we should find the defining equations of this algebraic variety. This is a test. So proposition, perhaps part of this is classical, but let me attribute there's a more refined statement. But what I'm going to say is probably classical. There's a more refined statement due to Landsberg and Wayman, is that the ideal is defined by the equations that you expect. How can I test whether my tensor has multilinear rank RST? This is equal to the tensors, in another definition, the same definition, such that the multilinear rank of T is less than or equal to RST. Okay, so how can I test multilinear rank? Well, I test it the same way I test rank for matrices, by minors. So the ideal actually is generated by the r plus 1 by r plus 1 minors of flattening to the a direction, so TA, and then the s plus 1 by s plus 1 minors of TB, and the t plus 1 by t plus 1 minors of TC. Okay, I want to do one more thing with this tensor here. What's the image? Well, the image of TC is just the linear span of C1. The image of TB is B1 and C1, or B1 and B2, sorry. And then the image of TA is A1 and A2. So I didn't say where this tensor lived in the beginning. It could have lived in a huge space, but it actually lives in this span of A1 and A2, tensored with the span of B1, B2. You could have seen this from the expression, but maybe somebody else gave this tensor in a slightly different set of coordinates. It wasn't so obvious that this was the case. Okay, so that's multilinear rank and the subspace variety and the equations that define the subspace variety. If you want to test multilinear rank, you test matrix rank for the flattenings. Okay, so one other fact about subspace varieties is that they contain the tensors of small rank. Well, let me define the algebraic variety first, and then I'll make the statement of containment in terms of algebraic varieties. Yes.
So the analogous thing holds for higher dimensional tensors as well?
That's right. So I can erase this and tensor many factors. It's very general. Okay. Also, this variety is very nice. It's normal with rational singularities, and its resolution is given by Wayman-Kemp desingularization. So there's a lot about this variety that we know. Okay. And then, of course, appropriate size flattenings for all the other ones. Okay, so the next algebraic variety that we want to consider is called the Secant variety, named after classical Italian geometers who studied these things over 100 years ago. So I'm going to take the Secant product, the product of three projective spaces, to the tensor product of all of them, which is going to take an element x, an element y, and an element z to the class of their tensor product. Okay, so the Secant product is the image of this map. We'll just denote it Secant PA cross B cross PC. And it's equal to also the tensors that have rank 1. This is a nice variety. It's smooth, it's closed, it's homogeneous for GLA cross GLB cross GLC, and it has many other nice properties. So this is the variety, algebraic variety of rank 1 tensors up to scale. The next variety we need is called the secant variety. Okay, so remember a tensor has rank r if it's the sum of r rank 1 tensors. So we might think about the algebraic variety of classes of tensors So first of all, is this an algebraic variety? It's not actually an algebraic variety unless we take the Zariski closure. Okay, so space, so this is sigma r of PA cross PB cross PC. This is the Secant product. Okay, so this is the secant variety of the Segre product. And more generally, you can define the secant variety if you have any x inside of projective space, algebraic variety. Sigma r of x is just equal to the class of points in Pn such that there exist x1 to xr points in x such that p is equal to x1 plus xr. That's the secant variety of the given variety. Okay, so in the homework there's a couple of exercises I think to show why this variety is not closed. Example of tensor which, okay, so we say that these guys, these tensors, define the notion of border rank. So it's a little bit odd. The tensors on the border don't have rank R. It's kind of opposite of what you expect. So call border rank all the tensors who, up to a limit, in Zariski sense or even a Euclidean sense, have rank R. So most tensors we expect in this space would have rank R, but then some of them could have different ranks other than R. Okay, so the next thing I want to talk about is what to expect about ranks. So if somebody hands you a tensor in a given space, you should be able to tell them what the rank probably is. They give you a random tensor in C10, tensor C10, tensor C10. What should you tell them the rank is? If it's just random. Well, let's figure this out, okay? We're going to use algebraic geometry to determine what to expect. So what we need is, so we want to know about the expected rank. So, and why do we want to do this is because, well, the most naive way to solve the tensor decomposition problem is to guess a rank and then try to solve an optimization problem defined to you by the tensor decomposition equation. So try to guess first R and solve or maybe optimize for some of your favorite norm. Okay, so both of these problems are extremely difficult, but if you can guess what the rank is first, you might have an easier time at finding the solution. So how do we guess the right rank? So one thing we should do first of all is we should figure out which subspace variety we want to work in, and then we're going to, after that, determine which rank we should expect. But let's do this first. So, yes.
Even if you solve this problem, it doesn't actually tell you that the rank is R, right? It only tells you that the rank is at most R.
Right. So you can keep going down. If you get really lucky and solve a really hard problem, you can try to solve a slightly easier problem with less variables and keep going down. Usually maybe you'd guess R is small and go up, or you could start with biggest R possible and go down either way, but try to guess the right rank and then solve. Okay, so what should you expect? So, well, let's suppose we have an algebraic variety here in Pn, which is linearly non-degenerate, so it's not inside of Pn minus 1. then, well, the first secant variety, well, the secant points are just x contained in the second secant variety, and then up to some k, which is going to be equal to Pn. So if you keep taking higher and higher secant varieties of a given variety, as long as it's linearly non-degenerate, then it's going to eventually fill the ambient space where it lives. So the last k for which we can find a non-trivial inclusion, we're going to call that the expected rank. So when x is equal to the Segre, call this k the expected rank for A tensor B tensor C. Okay, so over C there's one expected rank, but over R, for instance, if you're interested in that question, there can be many, so they're called typical ranks. But over C, there's only one expected rank. So a typical rank is a rank on which there's a set, a positive volume, for which all the tensors in that set have that same rank. So even 2 by 2 by 2 tensors over reals can have two typical ranks, 2 and 3. Okay, so now we just need to figure out when does the secant variety fill its ambient space, and then we'll know what to expect for the rank.
Does the expected rank have some distribution where we can say that expected rank equal to expectation rank under this distribution?
Can you say a little louder? Yeah?
Does expected rank, can you define some distribution over Pn so that random rank of tensor will be equal to expected rank?
Yes, yeah. If you choose the entries of your matrix randomly, then you will expect the expected rank for appropriate choice. Because the previous ones have smaller dimension, so they have measure 0 in any probability measure that you put on the space. Okay?
He was asking what distribution you choose the entries randomly
It
from.
does. I don't think it matters. That's the point. Pick any distribution you want, and for that distribution, the tensors of smaller rank have measure 0.
Well, you just have to have one that's going to meet any open set. One so the selection will meet any open set. Because you can probably come up with something where you find a subspace. Like say, selecting all of them equal without perfect.
I see. Right. So you want to be a little bit careful. I want to use the distribution where I work through the secant variety and I parameterize points on this space by writing actually a sum of k points. So I don't work with the probability distribution quite so much, so you can't really say something authoritative. Okay, so when does k Okay, so in order to determine this, we're going to determine this by computing dimensions. So I prefer the differential geometry approach to dimension, which is dimension of the tangent space. So first, let's compute the dimension of sigma 1 of x, which is just this Segre. So what we're going to do is we're going to pick a general, well, the Segre variety is homogeneous, so every point on it's general. Pick a general point, P, which is going to be, for our purposes, x tensor, y tensor, z. Okay. So pick a general point here, and we're going to compute the tangent space at x which is going to be an affine space, and we'll subtract 1 for the projected dimension. And how do we compute the tangent space? So let's do it in the example of the triple Segre product. So we're going to pick a curve. Okay, so we pick a curve like this that's on the Segre product. And the definition of the tangent space is all tangent directions to at this point. So I have a curve, and I'm going to take the collection of the tangent directions at 0 for these curves. So what I mean is that I want x of 0 to be equal to x, and y of 0 to be equal to y, and z of 0 to be equal to z. And while I'm at it, let me tell you what the derivatives are going to be, just denoted x prime, y prime, and z prime. Okay, so pick a curve like this. So then the span of all of the tangent directions of a curve through my point on my Segre product is just going to be, well, gamma prime at 0 is equal to x prime tensor y tensor z plus x tensor y prime tensor z plus x tensor y tensor z prime. Okay, so if you work through the product rule for derivative, still works over tensor products. So this is what a general tangent vector looks like, and we take all of them. Looks like this. Well, I can pick anything in the first direction, tensored with my point y, tensored with my point z, and then anything in the second direction, x tensor b, tensor z plus x tensor y tensor c. And really I should put the linear span of x, y, and z, but the tensor product is linear. So, okay, so I would be tempted to write direct sum, but these vector spaces are not disjoint. Not disjoint, so actually I should write this as x tensor y tensor z. This occurs in all of them. And then take a mod x tensor y tensor z, direct sum x tensor b mod y tensor z, direct sum x tensor y tensor c mod z. Okay, so now I know the dimension of the Segre product. It's the sum of these dimensions. Okay, so that's the dimension of the Segre product. It should be exactly what you expect. It's just this product. Okay, so this means that the expected, well, let me do one more proposition, which is the most useful tool in all of this, so let's write it down carefully, called Terracini's lemma. So that's how I compute the dimension of the tangent space, well, compute the tangent space of the Segre product. What about the tangent space at some point of this secant variety of x? So Terracini's lemma is the most useful tool in determining dimensions of secant varieties. And it's essentially just the sum rule for taking the derivative. So Terracini's lemma says the following, that if p in sigma r of x general, and x1 to xr in x also general, then p is the sum, then the tangent space to my point of the secant, tangent space of the secant variety at my point P is just the sum of the tangent spaces. This should be exactly what you're expected because the points on this variety are just sums. So we take the derivative, we take tangent vectors at the sum, and we get the sum of tangent vectors. So maybe this is best seen by an example. So let's compute let's find out about 2 by 2 by 2 tensors. Okay, so this is sigma 2, P1 cross P1 cross P1. So this is inside of P7. Okay, so first of all, there are tensors of rank 2. Rank 1 tensors don't fill up the whole space, right? Because the rank 1 tensors are just 3-dimensional, but I'm inside of P7, and P7 is 7-dimensional, so the rank 1 isn't filling. But I want to know, can I prove that these are equal? They are actually equal, so let's compute the tangent space at A1 tensor, B1 tensor, C1 plus A2 tensor, B2 tensor, C2. Trust me, this is a general point on the secant variety of this guy, secant. Okay, so I apply Terracini's lemma. This says that I need to take this tangent space is going to be A1 tensor, B1 tensor, C1, direct sum with A mod A1. Okay, so that's the first one, and then, right, so then I write the second one, and then we'll leave space. I think you see how this is going. Okay, so that's the tangent space at this point. And now I want to count dimensions. So I think it's slightly easier to count just the indices which occur. So all indices are either 1, 1, 1, or 2, 1, 1, or 1, 2, 1, or 1, 1, 2. That's what occurs here. And two-dimensional vector spaces, these are the possible indices that could occur. And then these are all indices 2, 2, 2, 1, 2, 2, 2, 1, 2, and 2, 2, 1. So just by writing down the indices of the vectors which can occur in a basis, it's very clear that these two Hamming balls, this is a Hamming ball of distance radius 1 around the point 1, 1, 1, and this Hamming ball of radius 1 around the point 2, 2, 2. These two Hamming balls don't intersect. These two tangent spaces don't intersect. So therefore, the dimension of this space is the sum of these dimensions with minus 1 because we're working over projective space. So this is actually, this tangent space is C8. And so this means that the two varieties are equal. Okay, so the last thing about what to expect and test for border rank, I think are going to have to wait until the next time, but I think I can tell you what to expect for number of decompositions. And then I'll be out of time. So how many decompositions should you expect for a given tensor? How many solutions should you expect in a system of equations? Oh, I forgot the punchline. So in general, we expect that the dimension of sigma r PA cross B cross C. Well, I need to choose R points from this space. And then I need to choose a point on the R plane which they span. That's what I expect the dimension is supposed to be. So before I say how many, I think I'll actually hold this till next time. Let's say the expected rank of a given tensor. So we expect sigma r to fill P A cross P tensor C when, okay, let's solve this. This is R times M plus N plus P minus 2 minus 1. When R plus N plus 1, whenever this exceeds M times N times P minus 1. So then we take the ratio, so we want R to be bigger than or equal to M N P divided by N plus P minus 2. Okay, so now, if somebody asks you what rank to expect over complex numbers of a tensor that's size M by N by P, then whenever R is larger than this ratio, you should expect, well, the smallest R that satisfies that, that's going to be the expected rank. Now, there are exceptions to this, and we don't even know what all the exceptions are. We have a guess what we think they are, but
in that case, oh, sorry.
We do not know all of the exceptions to this rule. And it's a study of area of active research, and then also for more than 3 factors. Also very interesting. There's several people in the audience who've worked on this problem. And next time I'll start with symmetric tensor decomposition. I'll talk about what to expect for a number of decompositions, and I'll talk about algorithms for tensor decomposition. So that's all I have for today. Thanks.
Questions, comments?
So you're saying this dimension is not always true?
That's right. That's why I never said this is the dimension. Could be wrong, right? For instance, matrices. Try that example. See what you get. Maybe the smallest example where it fails, try this one. 4 factors.
Already with 3 factors.
There's some with 3 factors as well. So how about P2 cross P2 cross P2, and then sigma 4. This is expected to fill, but it's actually a hypersurface. Strassing's degree 9 hypersurface. So the expected number, you expect this to fill the ambient space, but it actually fails to fill the ambient space because there's an equation which vanishes on this variety. So I didn't have time to talk about equations for tests for border rank. Maybe if there's time, I'll talk about that next time as well. Yes?
So where does it go wrong? So Terracini's lemma is still correct.
So Terracini's lemma is still correct, but we're so lucky that in this case, the vectors in the tangent space are always given by, well, in this case, Hamming balls. The indices are given by Hamming balls of a certain radius 1, centered around the point that we started with, but those Hamming balls don't have to fill, like, disjointly fill the ambient space. They could overlap. Right? So especially like take C, suppose C were 1-dimensional instead of 2-dimensional, then I would expect there to be an extra vector here maybe, but then they're going to overlap in this case.
That's why you were careful to write plus and not direct sum.
That's right. That's right. So I put plus here as well. So in fact, this is a direct sum, but maybe it will fail to be a direct sum.
I guess you can understand these failures as surprisingly, that's not a direct sum in the cases of the failures.
That's right.
So that if n equals p, then that p2 cross p2 cross p2 is the unique time where it fails. That was proved by Strassing.
Maybe I ask a question about the
I would
subspace.
Lichtheit. Strassen and Lichtheit. Sorry.
The subspace variety.
Okay.
So if we take all the flattenings and
Yes.
then we take the minors of a given size, they together generate the correct prime idea, or generate a prime idea.
That's right.
So suppose I just take some of the flattenings, right? So I have an n-dimensional tensor. I take a collection of splits that I like. These things may not be irreducible. Are there nice examples where they're reducible? Has this been studied?
Okay, so I know
Take
a
some
paper
of-
of yourself with Drysma maybe and Zwernick and so on, where you studied in-between varieties, and those are examples of the things that you're mentioning. Very interesting. So suppose I just, yeah. So if I just pick one direction for the flattenings, then I'm just looking at a variety of matrices of lower rank, so that's irreducible, and there's a lot known about those. And then maybe I pick two directions of flattenings instead of just one, and I could study that variety. The first place I would look for a way to solve these problems would probably be Bierze's book about the rank varieties in his book. But I forgot to mention this, but subspace variety RRR always contains the secant variety. So this is why I brought this up in the very beginning. I forgot to mention this fact. So the first check whether you have border rank R or not is first check if you're in this subspace variety, as long as it's non-trivial. There are a lot of interesting questions like this one. I think that'd be a very interesting thing to study and actually write down all the specific cases. If you have a 3x3x3 tensor with two flattenings equal to these guys. But in general, I think that if you ignore one of the flattenings, then you're just going to look at sub RRP, for instance. This is just conditions, rank TA less than or equal to R, and rank TB less than or equal to R. And then P is just general. So this is an irreducible variety, and it's defined by those equations, prime ideal.
Suppose you have a partially symmetric tensor, all right? How can you go ahead and look at the flattenings of this guy? You wouldn't have to look at all the flattenings, you just have to look at the flattenings that aren't the symmetric parts. And then what can you say about the variety?
So this is anticipating next lecture, but let me just mention it since you asked. Suppose I have SimDV from Lensberg's lecture yesterday in the computer science department. This is symmetric tensors. So this means that Ti, J, K many indices is equal to T sigma I, sigma J, sigma K for all sigma in the symmetric group on D letters. Then a flattening is just a map from sim D minus E V star to sim E V. And I'm going to treat all the vector spaces the same. So I'm lifting this guy inside of sim D minus E. I break the symmetry. Think about it as a tensor inside of sim D minus EV, tensor sim E of V. And then write down the matrix associated to this. This is sometimes called a Hankel matrix, a catalecticand, or a symmetric flattening. Now, if you have a tensor that has some partial symmetry, you can break the symmetry or not break the symmetry and write down a partially symmetric flattening depending on how you want to split these up. So there's always these kind of inclusions, and there's even more general inclusions than that, which sometimes give more interesting equations for secant varieties, for instance. But I will talk more about this in the second lecture.
Question. You mentioned there are many typical.
So let's look at this one here, this example. Typical ranks over
Yes,
R, right?
yes. Is it that you don't have this expected rank over other?
So in this case, sigma 2 P1R plus P1R plus P1R has two typical ranks. And the picture here is really nice. You have, let's imagine this is my, R2 by 2 by 2. And the space is cut by a single hypersurface called the hyperdeterminant. And on this hypersurface, so the hyperdeterminant, the 2 by 2 by 2 hyperdeterminant, the ranks are going to be 1, 2, or 3. And this cuts the space in half, roughly in half. Not quite in half. And then over here you can have rank 2, and over here you can have rank 3, and this is real rank. And then maybe the volume of this space is probably like 30%, and this is 70%. I don't remember the percentage, it depends on your distribution. Right? So it also says, well, so if I randomly throw a dart at 2 by 2 by 2 real tensors, sometimes I'm going to get rank 2, and sometimes I'm going to get rank 3. And then very rarely I'll get a rank 1 on this surface here. And moreover, it also explains why you can't approximate something from rank 3 as something of rank 2. Because if I try to do that, I run into this hypersurface, which is cutting my space in half. So approximation problems can be very tricky because of this sort of behavior.
You can think of this as analogous to the way that polynomials in one variable have different numbers of real roots. There's a discriminator hypersurface dividing into pieces, and each open set in the complement you have a fixed number of real solutions.
But you can approximate something rank 2 by something rank 3, right? Or a sequence of rank 3 things?
You want to take something that has rank 2 and approximate it with more terms?
Yeah.
Of course.
But it just doesn't look like you could do that from the picture.
Well, I mean, I'm saying rank exactly 2, but I could have written this in a redundant way and wrote it as rank 3. So when I wrote rank, I should have written it has rank less than or equal to this number. I should have said it's rank this if there's not a smaller expression. But right, so what Frank said is true. This hyperdeterminant also has an interpretation of discriminant. And when this discriminant is positive or negative, you're going to land in one of these chambers.
Maybe a question. So you mentioned as a result the ideal of subspace varieties, which is given by this minus of the flattening. So do we have a good description of the relations of those?
So the minimal free resolution, not just the first syzygies, but the minimal free resolution of that ideal is given by a twisted causal complex, and all of the details are in yours book, but you can write down a certain partial desingularization by the product of Grossman varieties, and then you can actually explicitly write out the representations for every stage of the minimal free resolution. So we have perfect understanding of the relations as well.
So we know in this free resolution, we know all the representations that occur.
That's right. Yeah. So you can compute them all by Bott-Burrell-Bay theorem, for instance. So what gets really hard, though, is Matt's question. When we start working with other types of tensors, this problem is very hard. So if you look on the last page of JM's book, you'll find an example for skew-symmetric tensors where the result is much more difficult than this case. But this case is this triple Segre product case, or many factors, just no extra symmetry, is fairly well understood.
No more questions, no more comments, so let's thank the speaker again.